All right, this is lecture 20, part 1, graph basics. So in this short lecture, we're going to review some of those graph terminologies and also Euler's result, as well as a simple proof regarding the sum of vertex degrees. So you have seen graphs in many places, for example, maps and social networks. In terms of social networks, you can think about each node as a vertex set. And each node would be, say, a friend in your social network. And then there's an edge, which is, if two people are friends, they form an edge between them. On the right-hand side, we show a sample example of a graph where the nodes are cities, for example, Madrid, Paris, Rome, and London. And then there is an edge connecting them, and where the weight corresponding to the distance between those cities. Okay, so the commonly when you actually represent a graph, you have graph G, and it has a vertex set and an edge set. Okay. The next thing is that when you look at this graph, the edges can be directed as an example below. For example, we can look at the distance going from Madrid to Paris versus from Paris back to Madrid. They have different distances. Let's say this is the driving distance or flying distances. Because they don't take the exactly same path, they might have different distances. Okay, so in this case, when you have a directed edge, the ordered pair will represent the edge. For example, the edge going from Rome to Paris is not the same as the edge going from Paris back to Rome. So from Rome to Paris is this edge, and from Paris back to Rome is this edge. And whether an edge is directed or not, they can still come with weights attached to them, which basically correspond to some notion of a cost of going along that edge. So when the edges are weighted, it's called a weighted graph. Otherwise, it's called an unweighted graph. So there's an example regarding what's called a simple graph. Okay, so in this example, a simple graph is one without loops or multiple edges, called simple graph. So the picture shown on the right-hand side is actually not a simple graph, because we have a self loop, and between Paris and Rome, there is multiple edges. So in order to make this a simple graph, we need to remove the self loop and removing one of those two edges to make sure that there's only one edge between two things. Okay. Again, let's recall if a graph is undirected, then an unordered pair will correspond to the edge. Okay. All right. Next thing, which we are going to see again in part 2 of this lecture, is a concept of walks, trails, and path. Let's start with the concept of a walk. Okay. A walk is a list of alternating vertices and edges where each edge connects its neighboring vertices in the list. For example, if I go through the yellow walk going from Madrid through the edge 1, go to Paris, go back, let's see. If I go from Madrid to Paris, from Paris making a self loop through edge 6, and then back to Paris, and then go to London, that is a particular walk. And then the walk, the length of a walk is its number of edges. Okay. And then a walk is trivial if its length is 0. Finally, if the first and last walk is the same, then the walk is closed. For example, if I drew a different color, if I go from Madrid to Paris, from Paris to Rome, and from Rome back to Madrid. This is a closed walk. Okay. Now the next concept is the idea of a trail. So a trail is a walk with no repeating edge. Okay. So let's look at what is example of a trail. So remember, it cannot have repeating edge. So if Madrid goes to Paris, Paris goes to Rome, then Rome go back to Paris, and Paris go to London. This is a trail, okay? And then the next concept is what's called a circuit, okay? So let's look at a circuit. The circuit has to be a closed trail. So first of all, a trail cannot have repeating edges. A circuit is a closed trail, so you start with the same vertex and come back. So for example, going from Rome to Paris and Paris back to Rome, that is a circuit. Okay. The next concept is a pass. Okay. So what is a pass? Let's use yellow again, a pass. So a pass is a walk with no repeating vertices. So for example, if I go from Madrid to Paris and to Rome, that is a pass because we only visited each vertex once. Okay. And finally, a cycle is a non-trivial closed trail in which the only repeated vertex is the first and last one. So again, think about what might be example of a circle. In here, it's for example, go from Madrid to Paris, right? It has to be non-trivial and closed trail. So it has no repeated edges, and the only repeated vertices is the first and last one. So Madrid goes to Paris, Paris goes to Rome, Rome back to Madrid. That is a circle. Okay. All right. Now, if you have a graph, there is a concept of what's called incident. Is incident with a vertex. So, for example, if this is my graph, A, B, C, D, where my vertex set is A, B, C, and D, and an edge set is, say, let's say this is edge E1, this is edge E2, this is edge 3. So in this case, edge E1 is incident to A. Same thing with E2 and E3. So all three edges is incident to A because they have A as an endpoint. Now the second concept is the degree of a vertex. Is the number of times it appears at the endpoint of an edge. So in this particular case, the degree of the example I just drew, the degree of this vertex A is equal to 3 because it's the endpoint of 3 edges. And then there's a concept of connected component. A graph is connected if there's a walk between any pair of distinct vertices. So for example, this is a connected graph where for any vertex, I can reach any other vertex. However, this whole thing is not a connected graph because I cannot go from vertex A to vertex B because there's no walk since they're not connected. So second concept is that a graph H is a subgraph of a graph G if all the vertices and edges in H are also in G. So let's say this is my graph G with vertex A, B, C, and D. Then this is my graph H with vertex A, B, and C. Then I would say H is a subgraph of G because all the vertices and edges in H are also in G. How do I see that? A map to A, B map to B, C map to C. So all the vertices in H is also in G. Now, the edge AB is in H, HAB is in G, AC is in H, AC is in G, BC is in H, and BC is in G. So this is an example of a subgraph. Now, if H is a subgraph of G, H is connected, and then there exists no other connected subgraph of G containing H, then H is a connected component of G. Okay. So for example, in this example right here, that the subgraph AC is a connected component of G. Let's see, the whole graph G is a union of those things. And then the graph H is the one that contains vertex AC and the edge AC. The next concept is called Eulerian graphs. So a trail or a circuit is Eulerian if it uses every edge in the graph exactly once. So this is the most important part of the definition, is every edge has to show up exactly once. And a graph is Eulerian if it contains an Eulerian circuit. Okay. So one of the most important results surrounding Eulerian graph is Euler's result, which is theorem 2 in chapter 7 and theorem 5 in chapter 7. So theorem 2 says, if G is a connected graph, G is Eulerian if and only if every vertex in G has an even degree. So for example, a simple Eulerian graph is what I just draw here, where every single vertex has an even degree. Now for theorem 5, it says a connected non-Eulerian graph G has an Eulerian trail if and only if G has exactly two vertices of odd degree, and the trail begins and ends with these two vertices. So what is a simple example? If I have a graph, so this is an example where the only nodes with odd degree are vertex A and vertex B. And now the question is this graph contain an Eulerian trail? And please think about it, and we'll look at similar examples in part 2 of the lecture. So think about this as a take home. And finally, we have one last simple theorem, theorem 3 from chapter 7, that is about the sum of degrees for a graph. So for a given graph, the theorem says that the sum of the degrees of the vertices is equal to twice the number of edges. So sum of degree of all the vertices is equal to 2 times the size of the edges. So here, this means the number of edges in the graph. Okay, so it turns out for this particular theorem, there's actually a very simple proof. But before we go into the proof, let's look at what does this theorem really mean. Let's say I have a simple graph, which has 3 vertices and 3 edges. What is the sum of degree on the left-hand side? The sum of degree, I have node A, B, and C. Each one of them has degree 2. So I have 2 plus 2 plus 2. And on the right-hand side, I have 2 times E. The number of edges in this case is 2 times 3, which is equal to 6. So this is a quick check, that this theorem holds for a simple graph. But now this theorem actually applies to any graph. So how do we prove it? The proof is really the 4 lines showed before. So, actually, let's double check this as well to say, if I have a self loop for this graph, what's going to happen? So because I have a self loop, degree A have a degree 4, B has a degree 2, and C has degree 2, okay? So in this case, the right-hand side is 2 times 4 because there's 4 edges, okay? So again, this theorem holds for graphs with self-loop. So the first fact we know is that if I take an edge from a graph, it always has 2 endpoints. But even if it's a self-loop, it just happened to be the beginning and end point at the same point, but there's always 2. So the degree of a vertex basically counts those endpoints. And in summing up the degree of each vertex, we count each edge exactly twice. Okay? So what does this mean? This means that if I sum over all degree of the vertices, it's counting effectively twice the number of edges. Therefore, that's our formula we try to prove. Okay? So that's the end of part 1 of lecture 20. And part 2 of lecture 20 will come up very soon. Have a good evening.